Okay, I hope I adjusted correctly. So here is how we're going to apply those special case. First, we start from here. Because beta is small enough, we can apply the special case. So starting from here, so we start from z0. That's our first Euler point, and that's our initial value. And we apply Euler's method to this box. With this m1 and m2, m3, it's not quite shown here, but they serve as an upper bound. So that same number will work in here. So we're going to see that the first gap is created in here. So after you apply to the first block with the width beta, and the final gap in that first block is a gn, and this is the formula from the special case. G0 is the first initial gap, which is 0 in this case, and there's all the other part, m2, m3 are not exactly the maximum of that smaller box, but this still serves as an upper bound, so we can modify the proof with this one, where the alpha was 1 plus h times m3, which is an upper bound of the partial derivative, and alpha to the n approaches 0, and we have that property from before. Next thing we do, this is the gap at the end of the first block. We take that as an initial situation of the second block and apply the special case once again. Okay, I'm showing you the picture again. So this is where our initial value y0 tilde is. That's the exact correct solution. And z0 tilde was the n value of the first special case trial. So we take that as now a new initial value. So there's a little gap at the beginning even. Then we apply special case one more time. Again, it's m1 and m2, m3 are still serve as an upper bound. So we can apply that special case. The one thing you have to be careful here is the guaranteeing that all these, for example, z tilde k, which are the intermediate points when we apply special case the second block, we have to guarantee that those are within this box again. So that will be a slightly different matter. So I'm putting it in this form. Let me show you the picture again. Great, it fit down there. The zn tilde and yn tilde is endpoint in here. This is where we start, z0 tilde and y0 tilde. We started from here. If all those Euler points starting from here, if they're in the box, we have exactly the same result with the same constant m2 and m3. So the endpoint in here, gn tilde, the gap in the second block, it has exactly the same formula if those Euler points are in the box. So I'm showing, I apologize not showing the proof, but it is a fairly simple to simple relative to this whole thing that we were doing here. So I usually assign this as a homework problem. So I'd like to claim that this, if the beta is in this side, which is the part of the condition, or divided by 2 times m1, it is going to imply that all the zk tilde, let me fix that. Now it's fixed, and zk tilde is actually in between that a plus r and b minus r, which is the upper and lower bounds. And the reason I have a 2 here, and this will take care of, let me say that again, r over m1 will take care of pretty much all the increment of zk tilde, but because we start with a positive gap instead of 0 gap, we have to make sure that this beta is small enough so that the error that caused from the g0 tilde is not big enough. So that's the condition that we're putting in here. And again, it has to be some fairly small h. But with that fairly small h, and with this condition, we can show that the zk tilde anywhere in here doesn't escape this a plus r and b minus r. So this is where we can use this condition to guarantee that in that box. Now we're here at the end of the second block, and that'll be the gn tilde, the gap at the end of the second block, and then we take that as a new initial value, y0 hat and z0 hat, and start one more time. So let me show you the earlier picture. This part was there before and didn't have a chance to show everything, but I showed this part and that part. So this is the end of the second block, and we take that gap to each number as an initial value of the final attempt, and do the Euler method one more time, and then here is finally the final gap. So here we start from z0 hat and y0 hat and zn hat and yn hat, and that's going to be our final answer. And when we do that, we start from here. That's going to be our initial gap. Exactly the same situation, same bound and everything. So g n hat is bounded by this number. Here's a summary of the situation. G0 hat was the final gap of the middle block. The middle block was related with this initial value of that middle block, about using the same kind of relationship. And this tilde was actually final gap value of the first block, and this first block final gap is related through this inequality of the very initial gap, which is a 0. So we've seen that in our earlier video, this alpha to the n approaches some positive number, the value of exponential. So h is dominating, that approaches 0, that goes to 0. That makes this g0 tilde, that approaches 0, and that's exponential convergent value, that approaches 0. That makes g tilde, g hat 0 approaches 0. So that approaches 0, it's bounded, and that approaches 0, alpha to the n. That makes this finally gn hat approaching 0. So that's written here. Because this is finitely many blocks involved, this control will be sufficient to control the last gap to be approaching 0. So here's our picture once again, applying the special case a couple times with this careful control so that it takes care of the initial gap being positive, and using the same upper bound, and we were able to apply special case all the time, controlling that all the zk tilde and zk hat, they're always contained in this box, and we have the same technique applied to finitely many times, so that we can eventually make this one approach 0 at the end. Thank you. That was very difficult to absorb all this thing as an undergraduate student, probably, if you are an undergraduate student. But I think it is one very first numerical method you encounter to solve a difficult non-exact differential equation, and I thought it's important to see, for you to see that why this one works. And this is the typical analysis, and if you think about it, it doesn't really require fancy theorem or anything. It's just a careful analysis, and it is something we can do. So thanks for listening and for your patience. Thanks.